So today we'll talk about Compton Effect, and what this was about is about giving more properties to the photon and explaining the different experiments and different findings. And one of the main findings is the X-rays. So through the experiment that Hertz did, the photoelectric effect, he almost discovered the presence of X-ray, but then later on, it was fully discovered by William Röntgen, which is a Dutch physicist, and then he discovered something that up to that point was not known. It was an unknown radiation, and this is why he called it X, because something that we don't know, we call it X, and they call it X-ray. So it discovers that X-ray passes through some materials, but we're able to stop through some other materials. This discovery was used immediately and was put in place into medical field. And you probably have seen a picture of X-ray where you see the bones, and then you see all the configuration of the bone, but the flesh is not shown. So in this way, it gives them doctors a better view of why is it happening and what is it happening. What were X-rays? X-rays were tested to see if they were deflected in the electric or magnetic field. Since X-ray was not affected by either a magnetic or electric field, they were thought that they were either neutral particle or an electromagnetic wave. X-ray were known to penetrate into materials that had as small as 0.1 nanometers, so therefore the diffraction grating has to be with a distance between the gratings of less than 0.1 nanometers. Finally, in 1912, Bragg finally figured out that X-ray are actually part of the electromagnetic spectrum, and when X-ray produce a diffraction pattern, when X-ray produced a diffraction grating pattern through a crystal. Now, when electrons strike the anode, the kinetic energy of the electron is converted into X-ray radiation and heat energy. The minimum wavelength, or therefore the maximum frequency of X-ray, is when the kinetic energy of the electron is completely converted into X-ray energy. With using the principle of conservation of the energy, we can say that the initial electric potential is equal to maximum X-ray photon, because it is just an X-ray. So since it is an X-ray, then it is a photon. So what do we have here? The electric potential energy is equal to the energy of X-ray, or QV. QV is equal to HF, or HC over lambda. When the maximum frequency of the X-ray produced by a cathode ray tube is applied with a difference of potential energy, what is the frequency? So what is the maximum frequency of X-ray? When the difference of voltage is 30 kilowatts. Then again, the electric potential energy is equal to the energy of X-ray. The electric potential energy between the two parallel plates is measured Q times delta V, while the X-ray being a photon is HF, and 8 Planck's constant times frequency. And from here we can find that frequency is Q times V over H, or since we are dealing with the electron, so this will be 1 electron volt times 30 times 10 to the power of 3 to convert it into volts over 4.14 times 10 to the power of negative 15 electron volts. Or if we are writing what is the electron volt, so 1.60 times 10 to the power of negative 19 times 30 times 10 to the power of 3 over 6.63 times 10 to the power of negative 34. So then we figure out that the frequency is 7.24 times 10 to the power of 14 hertz. And this is the maximum frequency that the X-ray can produce when we have that difference of potential energy of 30 kilowatts. Now, when we have a cathode ray tube that operates with a voltage of 80 kilowatts with a current of 875 microampere, what is the intensity? What is the intensity? So intensity, which is the same as saying number of, now intensity of X-ray, number of photons per unit of time. And what is the minimum wavelength? Because maximum frequency will produce a minimum wavelength produced by this cathode ray tube. Now, let's first figure out what is the number of electrons that are hitting the cathode. Okay, so using the fact that the number or the charges, or no, using the fact that intensity of the current is the rate of charge, means that is the number of charges per unit of time, we can figure out that Q is equal to I times T, which in our case will be 875 times 10 to the power of negative 6 amperes times 1 second. Okay, because this is what it is saying here, that we are looking for what is the number of photons per second, okay, per 1 second. So then the charges will be equals to, let's figure out what is it in the calculator. I was having a brain fart. Okay. So now the number of electrons that the charge has in this case will be n times the elementary charge, which is from here we can find that the number of electrons is Q over elementary charge, which is 8.75 times 10 to the power of negative 4 over 1.60 times 10 to the power of negative 19. So the number of, why is this Why is this? Because the charges that are quantized are multiples of the elementary charge. So the number of electrons is equal to 5.47 times 10 to the power of 15 electrons. However, what do we know in the relation between photons and electrons is that the number of photons is the same as the number of electrons. Okay, because they have a one-on-one relationship, they are faith to each other. So we can say that the number of electrons this is the intensity, which means that the intensity of X-ray will be the number of photons over 1 second, which is 5.47 times 10 to the power of 15 photons per second. Okay, so now let's find the energy or the wavelength, the minimum wavelength that the photons have, using the fact that the electric potential energy is equal to the energy of the X-ray. So from here, QV is equal, since we have parallel plates, is equal to HC over lambda, because we have an X-ray that is at EMR. So then from here, lambda will be equal to HC over QV. So this will be the same as saying 4.14 times 10 to the negative 15 times 3.0 times 10 to the power of 8 over 1 electron times 80 times 10 to the power of 3 volts. So the wavelength will be 1.55 minimum, and this is minimum, times 10 to the power of negative 11 meters, or 155 nanometers. When the wave X-ray are unique because they have the ability to act as a wave and as a particle. So when they are X-ray as a wave, it has characteristics so that it penetrates in opaque objects such wood, paper, aluminum, human flesh, but not bones. Penetrates to opaque materials, but not bones. This is why it is widely used in medical field. And X-ray can be deflected by crystals. Okay, when they are acting as particles, X-ray can ionize gas so they collide, and then the electrons reach, since they have a high energy, can reach the ionization level, will cause electron emission in water by some process, by some process, as was even mentioned above, with that is known as the is the Röntgen and Bragg and everything that they did. So emission of electrons in water. And also will affect photographic plates. Okay. All this work led to the idea that, okay, so now we are dealing with a photon that has all those qualities. It's acting as a wave, it's acting as a particle, and so and so. And then in Compton was a very well-known physicist at the time, but he was intrigued by idea that if photon have energy, so tiny massless particles that have energy, why not momentum? And he derived the equation that is known now as the momentum of the photon. So now, what did we learn from the first unit is that momentum is mass times velocity. We know, and we will learn it later on the following lessons, that the energy of the photon, and for that matter of a particle, is mass times c squared. So we know this equation, which we will explain this equation later on. So now if we derive mass from this equation, so energy over c squared, and we replace it into the particle formula for momentum, and then we can say that momentum is energy c squared times v, which is c, because it is moving at speed of light, since it is EMR, then E over c. So now, if E over c, and what we know from the and we know from Planck's equation that E is equal to hf or hc over lambda, then we replace that. We say that momentum is hf over c, or f over c is 1 over lambda. Then we can say that momentum is h over lambda. Okay, or we can say, if we replace this equation here, then we will have momentum is equal to hf over c. Or even if we use the fact that wavelength is c over f. So now this is where we come to the formula that momentum of a photon is h over lambda, or hf over c. Okay, so now momentum or photon does not have only energy based on Planck's, that energy is hf, but it has even momentum. And this momentum, even though that is massless particle. Compton initially experimented with X-ray photons to bombard atoms, but the effect was so small and it was not measurable. And then Compton began to bombard electrons rather than atoms, and he measured the wavelength of the incoming X-ray. So we measure the wavelength of the incoming X-ray incident or initial, and the electron here. And then he was able to, so this was before the collision. And then what he noticed is that the electron was moving on one direction, and then you had a scattered wavelength X-ray that was forming an angle theta with the initial direction. And this was after the collision. So the collision between X-ray and a photon, X-ray photon and the electron was pure elastic collision. Remember what we said about elastic collision? We said that it's not only conservation of momentum. Conservation of momentum is applied, but even the kinetic energy is conserved. So now, when we are writing the conservation law of momentum, what we are saying is that momentum initial is equal to momentum of the electron after the collision plus momentum final of the photon. Okay, so this is momentum of incoming photon or X-ray and this is momentum of electron after the collision, and this is the momentum of scattered X-ray. Okay. So in that picture, what we have is momentum initial. If momentum initial is this one, vectorially, and this is before, and then after we had momentum of the electron and momentum of scattered photon, creating an angle theta, then this one here will be momentum initial of the initial moment of the initial X-ray. And then if we apply the conservation law of energy, we will have the incoming X-ray energy. So the, how can I say, incoming X-ray energy is equal to the kinetic energy of the electron plus the scattered X-ray energy. Or the energy of a photon is hc over initial lambda is equal to 1/2 mv squared plus hc final. And this is based on the conservation law. Using all those, both of those two principles, conservation law of energy and conservation law of momentum, we can draw the conclusion that the change of wavelength in the X-ray photon which is always final minus initial, is equal to HMC 1 minus cosine theta, where M is mass of electron, that is 9.81 times 10 to the power of negative 31 kilograms. And angle theta is the angle created through the X-ray scatters. So the angle created between the scattered X-ray and initial X-ray. Compton experiment became known as the Compton Effect, and he actually won a Nobel Prize for this, and shows that a photon of an electromagnetic radiation can be regarded as a particle with a defined momentum and energy. We know energy from Planck, but momentum. Photons have momentum and energy like a moving particle, but they also have frequency and wavelength as waves. So let's calculate the momentum of a photon. So what is momentum of a photon? With a wavelength of 455 nanometers. So momentum is h over lambda, or 6.63 times 10 to the power of negative 34 joules times seconds over 455 times 10 to the power of negative 9 meters. So momentum is 1.46 times 10 to the power of negative 27 kilograms meters per second. Have the same units as momentum that we have seen on unit 1. Okay. A photon of a light of 0. A photon of a light with a wavelength of 0.427 nanometers hits a stationary electron. So this is the assumption that we are doing here, that electron is stationary. The scattered X-ray, so this is initial, the scattered X-ray is 0.429 nanometers. What is the resulting speed of the electron? And what is the angle theta? So what is the speed of the electron and the angle theta scattered? Okay, so now to find the speed, we will use the conservation law of energy, because that is what relates the energy of so what we are doing here is elastic collision. So kinetic energy is conserved. So then we have the kinetic energy of the electron is equal to the change of the energy that the photon is under. So initial minus final, okay? Initial minus final. So the kinetic energy of the electron will be hc over 1 over lambda initial minus 1 over lambda final. So now what we have is the kinetic energy of the electron is 6.63 times 10 to the power of negative 34 times 3.0 times 10 to the power of 8, 1 over 0.427 times 10 to the power of negative 9 minus 1 over 0.429 times 10 to the power of negative 9. And then you will have a kinetic energy of the electron of 2.17 times 10 to the power of negative 16 joules. Now, based on the fact that electron is a particle, 2 mv squared, and then from here we find that the velocity is 2 times k over mass, or the square root of 2 times 2.17 times 10 to the power of negative 16, 9.11 times 10 to the power of negative 31. Okay, the speed is 2.18 times 10 to the power of 7 meters per second. Okay, and based on the fact that the change of wavelength, which is final, lambda final minus lambda initial, is HMC 1 minus cosine theta, we can find that cosine theta is 1 minus MC final minus initial over H, or theta is the inverse cosine of 1 minus MC, change of final minus initial over H. And if we substitute them, we'll have 9.11 times 10 to the power of negative 31 times 3.0 times 10 to the power of 8, 0.429 times 10 to the power of negative 9, minus 0.427 times 10 to the power of negative 9 over 6.63 times 10 to the power of negative 34. So angle theta is 79.9 degrees, almost 80 degrees. Okay, so this is Compton effect, or the scattered X-ray. Okay, this is the video for Compton effect.